Here is an integral obtained by use of differentiation. I've numbered it 1 because I hope to do a few more in due course. And this time, the integral we want to work out I've termed v, and it's equal to the integral between 0 and infinity, x times e to the power of minus ax times cos bx dx. Now, because there are 3 terms here, it's going to make doing it by parts a little bit awkward. So instead, what I've done is I've removed the x at the front and had a different integral, u, which is the same as the first one, but without the x at the front, and then proceeded to work it out. So we got this far. Right, the next step then, the first times the integral of the second, which is that bit between the limits 0 and infinity, minus the integral of the first differentiated, which is minus a e to the minus x, times the second integrated, which is sine bx over b. And then moving on, the first of these, that one there, is equal to 0. That's easily checked. And then the second one, the minus minus becomes a plus, and we've taken the constants outside, so you've got a over b times the integral between 0 and infinity, e to the minus ax sine bx dx. And then repeat the process of integrating by parts. So I've written down your a upon b in a bracket, and then inside, repeating the parts process. The first, e to the minus ax times the second, which is minus cos bx over b. But instead of writing the minus there, all I've done is invert the order of the limits. And then minus the integral between 0 and infinity of the first, or the differential of the first, minus a e to the minus ax, times the integral of the second, minus cos bx over b dx. Right, and then I've just simplified all of that. The first of those works out to this term here, inserting the limits, and the second is minus a squared over b squared times u, the original integral. So we've got u equal to a over b squared minus a squared times u over b squared, which enables us to work out what u is by quite simple algebra, and we end up with the result here. Now, this is the nice bit. When we differentiate this, the integral u with respect to a, not with x, not with respect to x, but with respect to a, what we will get is the integral v. And then using this bit here, which I've used with a tick, you just differentiate that by the normal quotient rule, and it comes down quite easily to this expression here. And that then is our final answer. Now, I just said, as a bonus, see what results when you work out what du db is. I'll leave that as a little exercise to yourselves.